Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine sending end voltage, current, power and power factor of a three-phase medium length transmission line using its nominal pi equivalent circuit when load details and values of transmission line parameters are given. A three-phase 50 Hz 150 km long line has resistance, inductive reactance and capacitive susceptance of 0.1 ohm, 0.5 ohm and 3 micromho per kilometer per phase. If the line delivers 50 megawatts at 110 kilovolts and 0.8 lagging power factor, we have to determine sending end voltage, current, power and power factor assuming a nominal pi circuit for this line. Let us first write down the given data. Power consumed by the load PL equals to 50 megawatts, that is equal to 50 into 10 to the power 6 watts. Line to line receiving end voltage VR line equals to 110 kilovolts, that is equal to 110 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 110 into 10 to the power 3 divided by root 3. That gives us 63,508.53 volt. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for power consumed by the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 50 into 10 to the power 6 divided by root 3 into 110 into 10 to the power 3 into 0.8, that is equal to 328 ampere. Load current may be expressed in polar form as IL equals to IL at an angle minus phi L, that is equal to 328 ampere at an angle minus 36.8699 degree. This may be written in Cartesian form as 262.4 minus J times 196.8 ampere. Given length of the transmission line D equals to 150 kilometers. Resistance per kilometer per phase R1 equals to 0.1 ohm. Inductive reactance per kilometer per phase XL1 equals to 0.5 ohm and capacitive susceptance per kilometer per phase BC1 equals to 3 micromho. Let us now calculate resistance per phase. R equals to R1 into D. Using values we get 0.1 into 150, that gives us 15 ohm. Inductive reactance per phase XL equals to XL1 into D. Using values we get 0.5 into 150, that gives us 75 ohm, and capacitive susceptance per phase BC equals to BC1 into D. Using values we get 3 into 150, that is equal to 450 micromho. that is equal to 4.5 into 10 to the power minus 4 mho. Series impedance per phase of the transmission line Z equals to R plus JXL, that is equal to 15 plus J times 75 ohm. This may be written in polar form as 76.4853 ohm at an angle 78.69 degree. We have computed series impedance per phase of the transmission line Z equals to 76.4853 ohm at an angle 78.69 degree and capacitive susceptance per phase BC equals to 4.5 into 10 to the power minus 4 mho. Let us now calculate capacitor charging current at the receiving end. ICR equals to VR into half of J times BC. Taking receiving end voltage per phase as reference, we can write VR equals to 63,508.53 volt at an angle 0 degree. Using values we get ICR equals to 63,508.53 at an angle 0 degree into half of 4.5 into 10 to the power minus 4 at an angle 90 degree. That gives us 14.2894 ampere at an angle 90 degree. This may be written in Cartesian form as 0 plus J times 14.2894 ampere. Now we shall compute current flowing through the series impedance. I equals to IL plus ICR. We have determined load current IL equals to 262.4 minus J times 196.8 ampere. Therefore, I equals to 262.4 minus J times 182.5106 ampere. This may be written in polar form as 319.63 ampere at an angle minus 34.82 degree. Now we shall calculate sending end voltage per phase. Vs equals to VR plus I into Z. Using values we get 63,508.53 at an angle 0 degree plus 319.63 at an angle minus 34.82 degree into 76.4853 at an angle 78.69 degree. That gives us 81,132.714 plus J times 16,942.366 volt. This may be written in polar form as 82,882.815 volt at an angle 11.795 degree. Now we shall calculate capacitor charging current at the sending end. ICS equals to Vs into half of J times BC. Using values we get 82,882.815 at an angle 11.795 degree into half of 4.5 into 10 to the power minus 4 at an angle 90 degree. That gives us 18.6486 ampere at an angle 101.795 degree. This may be written in Cartesian form as minus 3.812 plus J times 18.2548 ampere. Let us now calculate sending end current. Is equals to ICS plus I. Using values we get 258.588 minus J times 164.366 0.1558 ampere. This may be written in polar form as 306.346 ampere at an angle minus 32.4238 degree. We have obtained sending end voltage per phase Vs equals to Vs at an angle delta equals to 82,882.815 volt at an angle 11.795 degree, and sending end current Is equals to Is at an angle minus phi 1 equals to 306.346 ampere at an angle minus 32.4238 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 82,882.815. That gives us 143.557 into 10 to the power 3 volt or 143.557 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 11.795 degree plus 32.4238 degree. That gives us 44.2188 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 44.2188 degree. That gives us 0.7167 lagging. Now we shall calculate sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 82,882.815 into 306.346 into 0.7167. That gives us 54.59 into 10 to the power 6 watt or 54.59 megawatt. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine sending end voltage, current, power and power factor of a three-phase medium length transmission line using its nominal pi equivalent circuit when values of transmission line parameters and load details are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.